So, Luasi, you're asking the concept number 5, which is the concept regarding the deuteron, right? Let me see.
Yes, Prof.
Here we go. Okay. So this is the deuteron section, and we are going to go through this. Any other issues, guys? Let's focus on the deuteron, because the deuteron is a very important point. It's a very important idea because it will give us a lot of information. When a
Also,
system
what is the difference between the Yukawa potential and the Coulomb potential? And what is the VNN potential?
So let's go one by one. Okay, good. You're asking a lot of questions now. And so I know what the problem is. All right, let's go for the deuteron first. Right, Luasi? Let's go for the deuteron, and then we move on. So the deuteron, we have learned a few things that we are going to go through in a little bit. But in this case, we're going to study some nuclear properties from the deuteron. We are going to have more on the idea of wave function. Let me just put this right. And then we are going to also investigate how strong is the nuclear force, right? Or the strong force. For that we have a potential which looks like this. We have axis here and here, right? This is R. This is the radius of the nucleus, which, as we know, is equal to 1.2 a to the 1/3 Fermi, right? And we know that the binding energy of the deuteron, which is 1 neutron and 1 proton, is equal to the mass of the proton, right? Times 1, right? Because it was one proton. Z times the mass of the proton plus mass of the neutron times n minus the mass of the nucleus, in this particular case, the deuteron. And this is equal to 2.224 MeV, correct? Everyone knows that, right? So we have a level, which is somewhere here.
I think it's a -22.
No, the binding energy is always positive. Now,
oh, okay.
Now, what is good that you argue with me. You don't believe me, and that's the way it should be. So the binding energy is equal to the minus energy here. So this is the energy, so it will be minus 2.224, right? You see, this is 2.222, but the energy will be equal to minus 2.224 MeV, right? The binding energy is always positive. So this is an important concept, because this is the energy of the nucleus, and which is always goes in the other direction. And we also know that the deuteron has a 1 plus equal j pi, right? And today we want to investigate what is this guy here. What is this V naught, right? What is this potential? What is the depth of the potential? What's the depth? That's how strong is the nuclear force. What's the depth of the potential? for the deuteron to be bound, right? This is what we want to investigate. So this is minus V naught, right? Because this is VR here. So far, so good, right? So now we also investigated that for this, we know that the parity is equal to -1 to the L, and J is equal to L plus minus S, right? And from here, we deduce that L can be equal to 0 or 2, right? But that S must be equal to what, guys? What is S?
1/2.
Well, S is 1/2 per particle, right? Because they are for a fermion. But as we have 2 particles here, S will be equal to 1. So this can have a J equal 1, right? So this was what we discovered the other day, because the total S is equal S1, let's call this S1, or S plus S2, right? Which is either 1 or 0. So in this particular case, the 2 spins, the 2 1/2 are pointing up, which give us a total spin of here we go, a total spin of 1, right? So this we learned so far, and we learned 2 things, very important concepts about the nuclear force. That the nuclear force, right, is spin dependent, right? Remember that the possibility of L equal to 1 was not possible, because L equal to 1 here, it will give us a negative parity, right? Remember that. But we see a positive parity right there. Right, Garinchuti?
Yeah.
Correct. So now we know that the nuclear force is spin dependent, because what it does is actually coupling the proton and the neutron, so the spins are pointing up, right? So what else do we learn from here? These also tell us that the nuclear force is not a central force, right? In the case of a central force, we must have that L is equal to a constant of motion, right? In this case, the fact that L is equal to 0 and can be equal to 2 tells us that there's a possibility for the wave function of the deuteron to be here 1 plus is equal to an alpha L equals 0 plus beta. There's a linear combination of these 2 possibilities, and both has actually S equal to 1, right? So where alpha squared plus beta squared is equal to 1, and this actually is this possibility, the L equal to 0, is about 96%, and this possibility is about 4%. And there's a problem which will help you to do this, but this is a difficult one, and we keep it here as a bonus question, right? To solve the magnetic moment. Here we go. Yeah. The magnetic dipole moment of the ground state of the deuteron as a function of these constants, right? AS and AD, where you have the wave function, the 1 plus wave function, is equal as a linear combination of this L equal to 0 and L equal to 2, right? And this coupling is equal to this. There's a nomenclature there, but the important thing is that the square of the 2 constants must be equal to 1, So we make sure that we have 100% of the possibilities. So now we move on. Is so far, is this clear? This is a very important point that we have learned. We have learned the some nuclear properties of the nuclear force from the simplest case scenario, which is the deuteron, right? Questions here? What's it?
No questions, Prof.
Everything is understood, right? Guku. Molo, Johnny.
No question.
No questions. Good. All right, then we move down. Actually, we are going to open a new one. I should have started from the top. So, but doesn't matter. Let's open a new one, and we quickly go through the next idea of wave function. So let's put all the screen here. Let's maximize this. Let's go to the top this time. Here we go. Let's go to the center. Max. Yeah, so we have enough space. Okay, so as we just decided, you know, the wave function, we have concluded from the fact that J is equal to 1 plus J in this bound state of the deuteron, and this state, as we know, is let me just change here the color here. This state, as we know, it is this is R and this is R, this is VR. So we have a state which is at minus 2.224 MeV and has a 1 plus excitation. This is the ground state of the deuteron, right? So now we want to know more. Remember that the Schrodinger equation is giving us all the information that we may have about the nucleus, about the system, given the condition that given the limitation of the Heisenberg's uncertainty principle. So now we are going to have a problem. We're going to solve this potential as we have done in quantum mechanics. So we are going to solve the Schrodinger equation in this case. And we are going to study this idea of wave function, right? So for this, we're going to assume we have a central force, just to make the problem a little bit easier. So we're going to assume that L is equal to 0. So the central potential will vanish, as we shall see in a little bit. So, and we are going to determine what is going to be V naught. Right, we're going to we know that R is going to be 1.2 a to the 1/3 Fermis, and our problem is to determine what is V naught. What is that depth of the nuclear force for the deuteron to be bound? Remember, this is the deuteron, and it's bound in its ground state. So now what we do is the following. So we just write the Schrodinger equation for a central force. So minus I squared over 2m. So we're going to have actually, let's write the full in spherical coordinates is the partial derivative of this over r square, plus we're going to simplify this in a little bit because this is the h bar square. This is the central potential mr square, which again, as I say, for L equal to 0, it vanishes, plus the potential. This is basically the Schrodinger equation, times the wave function, which we're going to call R and L, because depends on N and L quantum numbers, is equal to E, R, and L. Okay, so this is the wave function, I mean the Schrodinger equation that we have in our lecture notes right at the beginning of this section. Right, where R and L is this one here, but the wave function, as we describe here, it is the combination total wave function that depends not only on R but also on theta and phi. And this is the situation that we have a radial part. We are going to focus on the radial part, and then we have something called the harmonic oscillator. I mean, sorry, let me see, the spherical harmonics, which they are tabulated, and we know then what they are. But we are going to focus on this part, on the radial part of the wave function. And this is what we have in the lecture notes. So for this, we're going to make a substitution, and this is a very important one. So we're going to assume that R, this radial function, is going to be equal to PR over R. This is going to make our life much easier in developing this the solution to the Schrodinger equation. Right, so this actually implies that this equation, the Schrodinger equation, will convert to something much simpler, minus h squared pi over 2m. Then we're going to have PR here. Actually, sorry, the partial derivative square of PR over R square plus VR, because we have this is 0 now, right? The central potential is 0, plus PR equal to E PR, right? So now we know for the conditions in our potential. Make this a little bit smaller so we see everything clearly here. We're going to have two conditions, one which is going to be here and 2. In condition 1, we know that for R less or equal than R, the function, V or R equal to minus V naught, right? So in that particular case, inside region 1, between when R is equal, and this basically in the potential, the depth here, we can simplify the Schrodinger equation, which is here, with this condition, and then we have that minus h bar square over 2m p. Let's make this 2 so it's easier, right? Minus E PR is equal to 0 because the potential is minus V naught, which is equal to sorry, we are no, I just confusing you guys here. Sorry, this is not the, I was confusing with the condition 2. So in V, in this case, we have minus h bar square. That's okay. Over 2m p twice because this, this is the second derivative with respect to R, and this is going to be actually let's multiply by 2m h bar square. Plus is going to be plus, let's do it minus, actually minus here, V naught, P the R, let's do it in a sec, equal to E PR, right? So this is going to be equal to simplify this differential equation on P twice plus 2m over h bar square plus 2m over h bar square V naught minus B. as again we have used the thing that B, the binding energy, is equal to minus E, right? And this is equal to 0, where this term is greater than 0. So these kind of solutions in quantum mechanics are a solution of a sign. PR is equal to A sine of K1R, plus B cosine of K1R, right? Guys, interrupt me if you don't follow me. So here we just got the potential, obviously, for this condition is equal to minus V naught, which we substitute here. And this, we just multiply everything by 2m h bar squared. So this term disappears here, but comes here. And actually by multiply by minus 2m over h bar squared. And then this becomes V naught minus B, where we know that E is, B is equal to minus E, right? So far, so good? Rasi?
Yes,
This
Prof.
is clear, okay? And then, as we know this from quantum mechanics, this is also equal to 2m over h bar V naught minus B. V naught minus B. So that's the wave number K. So now we go to condition 2. And condition 2, R is greater than R, right? We are outside the potential well. And for this particular case, obviously, VR is equal to 0, right? According to this here, right? So we are in condition 2, where the potential vanishes and is equal to 0. So then this has a different solution, but it is similar also. So we have the same with h bar over 2m p second derivative. Now this is 0, right? So this is just minus E p is equal to 0, right? Always this is PR and this is PR. So then we can again simplify this, and then this is going to be P minus 2mb, because we know the binding energy, over h bar squared times P equal to 0. And this particular solution of the Schrodinger equation is as such. PR is equal to, now we're going to change the constants, C E K2R plus D E minus K2R. Oh, right. So we have two functions. Which let me call this K2R, doesn't matter. Right, this is going to be two functions which look like this basically. These are two sine and cosine functions, and in this case we are going to have two functions which look like this for the exponential, and this for the E minus K2R, and this is going to be E to the K2R, right? This goes to infinity and this guy goes to 0, right? So it's important. That's why I draw always functions and see how they look like. There's a different plotting functions online. You just say, plot a graph, and you can plot all these things because it's always important to see how the graph looks like, right? And in this case, this K2, where is the pencil here? Let me just zoom in, because otherwise the pencil, I cannot see it here. So then in this case, K2 is equal to 2mb over h bar squared. All right. So now we have two solutions. Actually, let's see if we can. Right. So we have two solutions to the wave function depending on where you are in the potential, right? If you are inside the well, you have a sine, a wave function. If you have you are outside the well, you will have an exponential function, right? So now we try to solve this. Let's open a new page here. And now what we're going to do is to apply boundary conditions. Now we know the two functions, which were p in that region 1, right? And this is 1 and this is 2 outside the well. P of r will be a sine of k1r plus b sine of k1r, and in 2 we have that PR is equal to C E minus K2R plus D E K2R, right? So we have these two functions, and we are going to go for those boundary conditions that will help us solving for the wave function. So we have one boundary condition that PR goes to 0 as R goes to infinity. So for this to happen, out of these two equations here, what do we have to do? Obviously, I just drew this before. And this guy, EK2R, which goes to infinity, this guy cannot go to infinity as R goes to infinity. So this implies obviously that D must be equal to 0, right? This must be canceling as R goes to infinity. So D must be equal to 0, right? Is that clear? Guys, I want you to
Yes,
follow
Prof.
up. All right, so now we go back to the change of variable that we made before. And this is going to come very important now, because we have that in this case, PR R is going to be equal to PR over R. So let's investigate what the sign will do. We have the sign of, let's say, K1R over R as R goes to 0. Remember, the sine is 1 here at 90 degrees, and the cosine is 0 and cosine is 1 at 0 degrees. So if R goes to 0, this sine of 0 over R, which is 0. So this can be solved by L'Hopital, and the sine of K1R goes to K1R. And the limit of this, the limit of R when R goes to 0, this is going to be equal to K1R over R. So basically, this is going to be equal to K1, right? So basically, R of R is going to tend to K1, right? So another condition that is also in the lecture notes, we do the same thing for the cosine. We know the cosine now, RR will be equal to the cosine of K1R over R, which is equal, when R goes to 0, this will be 1, and this will be 0, so this will be infinity, right? So we're going to have infinities. Infinities we don't want. They're not easy to treat mathematically, right? So for that to be infinity, for that not to be infinity, we must, sorry, there was a cosine here, right? Guys, you need to tell me, if I make mistakes, this also must be 0. The B must be 0. Because the cosine, so that implies that B is equal to 0. right? Is that clear? Let me bring this. And it should be.
Yes,
Is this
sir.
clear? So D is equal to 0 and B must be equal to 0, right?
Yes.
So then the Schrodinger equation, the simplify themselves, because then now we have only P of R in 1 is going to be equal to A sine of K1R, right? Because B is equal to 0. And we're going to have in 2, in the range 2, we're going to have a PR is equal to C E minus K2R, right? Now that we have this, and remember the constants. The constants K1 is the typical thing that we always do, 2m V naught minus B over H bar square, and K2 I mentioned it before, which was 2mB, right? 2mB over H bar square. So now we need to study the continuity in P and P prime. For this to happen, the continuity condition at R equal to R, right? What's going to happen at this particular point here? Obviously, the wave here must come with an exponential here, and they have to merge. So this is what I mean by continuity conditions. In both the functions P and the first derivative of P. This is how we solve these problems in quantum mechanics, right? So we already have one possibility, which is A sine of K1R equal to C E minus K2R. This is one of the questions that we're going to need. But now we can do the first derivative of these guys. Let me see if we can. So we say that we have PR A sine of K1R. So let's see. Let's do quickly it again here. I should use this space a little bit wiser. I always have to. Here we go. Here we go. We're on the top now. So as I say, we have 1 and 2 possibilities here, right? And this is R. And for condition 1, we have that PR is equal to A sine of K1R, we say, right? And for condition 2, we have PR equal C A e to the minus K2R. And the continuity conditions, we have done already the boundary conditions, tells us that 1 and 2 must be the equal in this case. So A sine of K1R is equal to C E minus K2R. And now we go to the first derivative, and P prime of R is equal to A K1 cosine of K1R for 1 here, and for 2 we have that the first derivative is equal to minus K2 C E minus K2R, right? And according to the continuity conditions, this must also equal. So we have equation 1 here, and now we're going to have equation 2, which is A K1 cosine of K1R equal minus K2 C E minus K2R. Is that clear? Is that good?
That's good, Prof.
It's good, no? Seems to be good. K2 C A K2. Okay. Now, we can play with these two equations, and we can divide this by this, and then we have the a goes away, and we have sine of k1r divided by k1 cosine of k1r is equal to c e minus k2r divided by minus k2e minus k2r. So then this k1 goes up there. So we have that the tangent of k1r equals k minus k1 over k2. What happened with the c? The c is also move. Let me see what happened with the c. There was also another c here. The c also goes away, right? Yeah.
Yes.
This c goes away with this c, right? So then this is k1 minus k1 k2, and that's it. Solution is very easy, right? So this is the solution. The tangent, or actually the tangent, let's write it down as you write it down. In Spanish is tg, but as you write it down is k1 over k2. Right, this is the condition that we have finally, and this is equal. If we go back to what is k1 and k2, so the tangent of k1, it is equal, let's write it down. It was equal to the square root of 2m v naught minus b, right, over h bar square times r here. And this is equal to minus k1 over k2, which is minus v naught minus b divided by b. And this is the final equation. This is the final equation, which cannot be solved analytically for one particular reason. Let me see what happened here. This is not straight. I'm not writing straight here. So this is the final equation. So we're going to have a tangent. Tangent will look like this, right? And we're going to have these guys which come like that. So we're going to have solutions here, as you know, from quantum mechanics. But our purpose is to determine what is V naught. And this equation by itself is important because we know, actually this should be R here, because we are talking about, we assume that the boundary conditions happen when R is equal to the radius of the nucleus. So this is the radius of the nucleus, which is equal to 1.2 times 2 to the 1/3, because this is equal to A, right? In Fermi's. So what I want to say is that we have everything. We have B, which is equal to minus, actually plus, always positive, 2.224 MeV. And we have, basically we have this, we have this, we have this. And the only thing that we don't know is the V naught. But the V naught, it is in both terms, right? And this is what makes things a little bit more complicated. 2m V naught minus B divided by h bar square times the radius of the nucleus is equal minus, again, V naught here minus B over B. So we have, I like to write it straight, V naught here and V naught there. And this is actually what we want to know. What is the depth of that potential? What is V naught for the deuteron, this state, to be bound, right? So how do we solve this problem? This problem cannot be solved analytically, because basically we cannot take V naught out as a function of the others. You know, we have one term here, let's call it term 1, and let's call this term 2. So the way to solve this kind of equations is by using Excel or just writing a little code in Python where you are going to provide values of V naught. You're going to make V naught, and you're going to have a term 1, and you're going to have a term 2 here. And you're going to start providing values or to V naught, let's say 10. You know, and see, you will get a value here of whatever. I'm just guessing, let's get 2, and you get a value here of 5. So obviously these guys are different, right? So 10 is not a solution, right? So this is a process, a solution by iteration. So when we have 2 terms where we cannot get this one out, V naught, and we have a term 1 and term 2, which both depends on V naught. So we're going to change them to make it 5, and again we will be 1 and 6. I'm just guessing the numbers, right? We need to get these numbers right, as we know what is the radius. We know these terms clearly, right? We know all these terms. We know what they are. We know this. We know this. We know this. Remember, always it's important to get if there's a possibility to get the C square here somewhere. When we solve this kind of problems, it's always good because to remember are the units that we discussed the other day, right? The units of the typical, basically the typical. What is my pencil here? Yeah. The typical units of H bar C equal 197.3 MeV Fermi. If you can get those units there, that will be very useful. And as we know everything really. 2.224. The radius is 1.2, 2 to the 1/3 Fermi. And so you either get your Excel file or you make a Python script. It's up to you. But I want this to be done by Monday, okay, or by Tuesday. Or Excel file where you just play around and you solve this equation by iteration. Basically, you keep adding, let's say 15 here. Let's see whether this term is equal to this term 20, 21, 22, right? Until you find a term, a value which is actually equal, right? So these 2 terms will be equal, then whatever it is, 5 here and 5 there, or 15 here and 15 there. So whenever you find that these 2 terms, term 1 and term 2, are the same, then you have hit the jackpot, and you got your solution for what is V naught, what is the depth of the nucleon-nucleon potential for the deuteron to be bound, the ground state of the deuteron to be bound. And you will see that this value actually is quite typical of many other nuclei. And this is now, I leave it here for you to come up with a solution to the problem yourself. I mean, we have deduced the equations. We know what is R, we know what is B. So we need to look at the tangent to have a better idea. We need to look at the tangent, how the tangent looks like. And I give you a hint. So the tangent of something is negative here, is negative. So the tangent, when we look at the tangent, our solution must be on this, on the negative side, right? Because the tangent of this is negative. So whatever is this, the value must be such that it is within this range, right? If we look at the tangent, Let's see here whether we can. I was just drawing these equations here. I want you to see the tangent of x. All right, you see the tangent goes to 0 at 0, and here we have a pi. So between pi and here is, I think it's pi half. So minus pi half is probably here, and pi, let me see the tangent, how it looks like. Tangent of x. Leave this page. Ah, here we go.
Bro,
Tell me?
bro,
Yeah.
we try to use maybe the value of VO as like maybe 34 to see.
Here we go, we'll see. So the value here is pi half. Between pi half and pi, the tangent is negative. So your value of for that left term, term 1 must be between pi half and pi, right? To be negative. Say that again, Ganishuti, what did you say?
I was just saying if we could try to use the value of maybe 34 maybe or V0. See everything.
No, you have to. Who is that talking? So now you have to play with those values. Now you have to play and do it carefully. I'm just giving you a hint of where the range of the values may be found. Always you need to consider that the tangent of something, this something, V0 must be something, must be such that the tangent of that is negative. So the tangent of something negative goes between, we just deduce it now, between pi half and pi, right? It was just written right here. Yeah, between pi half and pi is negative here, right? But anyway, those are the things that you to speed up the process. But the Python script must be or whatever you do, the Excel file, whatever way you want to solve this problem. But I want you to solve it by interaction. Yeah, and this is the process where you have when you have an equation which cannot be solved analytically. This is how you do it. Okay. Solution done, and now it's your turn to do it properly and get me what is V0. That is due on Tuesday. Luasi? Luasi, everything okay? Any questions?
Everything is okay.
So
No,
did we clarify your ideas of the deuteron? Now everything is clear.
Can we go back to the 10?
Go back
To
to, I will go back. Yeah. Here? Where do you want to go back?
On, okay?
Oh yeah.
Okay. I just turn it off because of the echo of the sound. But if you need to talk, just come and turn it on, okay?
Luasi, what do you want here?
You must turn it on.
I don't know.
No, I was checking something. Okay, it's fine. I was
Right.
checking if we do have K1 and K2.
K1, K2, they're somewhere here in the before, right here. K1 and K2 are here.
Okay, it's fine.
Yeah. Right. So you see in K1, K2, when you divide them, the 2m hy squared, they go away. And that's why you have only these two terms remaining, right?
Yeah.
This is what you see at the end here. You see the V0 minus B over V. That's because we have K1 over K2, right?
Yeah.
All right, and so it is. We have learned a new way to solve a problem, a new mathematical way to solve the problem. I'm not going to finish it for you because I want you to do the work. and do it yourself so you learn how to do it properly. All right. Then Luasi, more questions you have before. You were talking to me about the